we've just changed the model, so we have the option of specifying by parameter in main what the city connection distance is. And I changed its default value to be 500. But more to the point, that allows me between experiments to specify what connection distance to use. So it's flexible. It's more flexible. It's parameterized and more flexible. And the way we did this is in main, we went down and we set it the connection range to be max city connection distance. Okay? We okay with that? Okay, ladies and gentlemen, we stand now on the cusp of greatness. Okay? We're going to do something really interesting now. We have migration going on between cities, according to connection between these cities. We have people connected in networks within cities. Now, ladies and gentlemen, we're going to put into place a mechanism to allow for infection spread. Okay? We're going to put in place a mechanism by which people will proceed through a history of infection, and we're going to that end, use these parameters that we added to main. Do you remember these parameters? We added them earlier: contact rate, duration of latency, duration of infectiousness, duration of immunity, transmission probability. Okay, now you may wonder, why aren't those living within person? If they varied, mark my words, if they were to vary according to different people have different contact rates, different people have different duration of immunity, we would readily put them in person because we'd want to vary them for different assumptions for different people. In this case, we would like to vary these parameters on a per experiment basis. We're going to run some experiments, some scenarios, and we're going to vary our assumptions about these. And the most easy way to do it there is they live in Maine. Right now, they're not varying on a per person basis. They could easily vary on a per person basis. We could have we could have all of them vary on a per person basis. It's just that for what I had in mind, we don't happen to do that. And by using one value for them, we can easily specify it in the experiment, which makes this example a little bit more compact to run. Okay, so ladies and gentlemen, I would like to go to person, and we are going to set up a state chart to capture their progression among stages of infection. Okay, so let's go to palette, and I would like to create a new infection state chart called infection state chart. Can anyone tell me how I'd do that? What do I need to drag into person? An entry point, a state chart entry point is right. This would be called infection state chart. Nope, not statement, state chart. Okay, infection state chart. Okay, ladies and gentlemen, this infection will proceed in a classic way: susceptible, exposed, infected, and recovered. Okay, and there will be a waning of immunity. Okay, so I would like you to put in place the basic mechanisms for it, except I will leave you with a puzzle. And I'd like you to muse about it over the next few minutes as you're building this. I would like exposure to infection to not necessarily lead to infection. Yesterday, we had, if someone was exposed to one of these messages, they got infected. And, I waved my hands and said, we're imagining exposure to an infecting dose is what was meant by contact. But here, contact is going to confer a non-unity chance of infection. In other words, it's not guaranteed you get infection if you're exposed. Right now, we set it at a particular value. We could have it be 1 out of 1,000, 1 out of 100, 1 out of 10, whatever. The same principle will apply. How do we structure the model to capture that? So let's put in place a susceptible state. Okay, Winchell or Alan? Susceptible. Okay. Okay. Alan, it's version 4 I just posted. Okay. It's coming at a great time. It's the hierarchical state chart model 4.
Yeah.
Yeah.
Doesn't say which. Oh, that's version 1.
Yeah. This Alan, this one here. You can, Alan, you can. Winchell pointed out you can frob this thing, and turn it into a list view, and it will show the full names.
That's better.
Yeah. That's Winchillian innovation. Okay, so this is susceptible. Okay, and now we're going to put in place an exposed state. Exposed. Okay, and next we're going to be put in place a what state? Anyone? Infectious or infective, yeah. Either of those would be fine terms for it. And next, a what state? Recovered. Okay, good. Okay, ladies and gentlemen, you should know how to do most of this right away. So what we want is, ladies and gentlemen, we want to have, moreover, and I'm trying to give you a higher level description and seeing if I can challenge you a little bit to build those skills from yesterday. I want to have people of different colors for each of these states. I want them to be in succession, respectively, green for susceptible. I want them to be yellow for exposed. I want them to be red for infectious, and I want them to be magenta for recovered. Okay, so let me throw you some softballs here. Okay, slow pitches. Exposed to infectious. What do you think this is here? What sort of transition might this be? Well, we could actually represent it two ways. We could represent it as a rate transition. So you have a certain probability of transmission per unit time, as given by 1 over the duration of latency, or we could have exactly the duration of latency. Okay, given viral dynamics imposed and so on, I'm gonna make this I'm gonna call this transition exposed to infectious. I'm gonna call it completing latency, and this will be a timeout transition with a timeout of main dot duration of latency in days. Okay? Completing latency transmission. That's from exposed, ladies and gentlemen, to infectious. Please mark this. I'm leaving this susceptible to exposed as a puzzle for you. How are we going to have only a certain chance of transmission? Okay? How about infectious to recovered? What do we want for that?
If you want these people that have been exposed but don't actually become infectious to go back to?
Actually, this exposed here indicates latency. It's actually a term that's often used to indicate someone who's not yet infectious, but they are infected.
So they're the other exposed then?
Well, yeah, okay, great point. So
where do you want them to go to?
They'll stay susceptible.
They want to go back to susceptible?
Yeah. And you've got the key idea here. We need them to kind of see, okay, they get exposed, and then they check, am I infected? If not, I go back to susceptible. That's what's going to happen. And we're going to need a key construct, a key state chart construct to capture that conditional nature of it. And we used it yesterday, although in a different context. We used it to distribute people among initial states. A branch. We're going to implement a branch. So why don't we do that one next, okay? Since this is the heat of the moment. Okay, so let's go susceptible. This will be called, I'm going to call this transition exposure. So I'm being exposed to the bug, right? Okay, the instructor sneezed around me or coughed around me. Great. Okay, and then we want a branch. Now, this branch is going to go to two places. What are the two places to which it will go? Whither will it go? Will it go to infectious? Will it go to recovered?
Exposed and
Good.
susceptible.
Exposed and susceptible. So I'll put this one back to susceptible. I'll say by default they go to susceptible, but they go to exposed with a certain chance. How did I do that? Ladies and gentlemen, I dragged in a transition here. I called it an exposure transition. I dragged in a branch. I dragged in then two other transitions, from the branch back to susceptible and the branch to exposed. Now, this will be the default, so we have to specify a condition for this one. And this brings us to an important AnyLogic lesson, ladies and gentlemen. This brings us to an important skill to have in AnyLogic. This transition will be called infection, no less, ladies and gentlemen. And it'll be based on a condition. It's not the default, it's based on a condition. And what will that condition be? It will be, we're going to flip a coin. This is going to be a Bernoulli trial, as we say. We'll flip a coin with a certain probability it will be heads. They'll get infected. And what will that probability be? Can anyone say?
Main transmission.
Yes, random true main dot transmission. Now this random true, all that does is it returns true with a certain probability, generates true with a given probability p. So that's how we generate a Bernoulli trial in AnyLogic. We say random true. So it's going to return true with this probability. Okay? How do I know that? You can go look at it. Random true. Generates true with a given probability. Okay? Alternatively, you could have drawn a value uniformly from 0 to 1 and checked if it's less than p. But that's what we want. With that probability, they will get infected. Okay? Now that's going to allow us to vary that probability in main. Ladies and gentlemen.
So now you basically
Okay? Do what people want me to show that for longer? So let's be clear. Someone here gets exposed. Oh, ladies and gentlemen, I've left a key thing blank here, or a key thing I haven't attended to. What sort of transition will exposure be?
A message.
It'll be a message transition. Now, what sort of message that will be, we'll come back to. Right now I'm going to leave it unconditional, because I'm deliberately going to introduce a problem, and you're going to help me solve that problem. Okay? It's going to be unconditional, just like yesterday. Remember that? Yesterday. Okay, great.
that was a lifetime ago.
Okay, ladies and gentlemen. Yeah, right. Okay, ladies and gentlemen. So now we have this machinery set up here. This represents the conditional nature of exposure. Sometimes exposed infects me. Sometimes exposure just leaves me susceptible, exactly like Dina had observed. Okay, next, ladies and gentlemen, for the transition from infectious to recovered, what would you like? Would you like this to be exponentially distributed with a certain duration on average, or would you like it to be a timeout? Maybe we'll make it exponentially distributed. Some people get better faster, some people less. So if we want an average of the duration of infectiousness, we need the rate to be 1 over that. Now notice I put 1.0, folks. I do this in my boot camps, and there's a lot of cases where it's gratuitous, but I do it to prevent my students from making a terrible mistake. A mistake I see in computer science students of note. Okay? Let me tell you a sad fact. Okay? And I hate to relate this to you. It's a little bit sobering. I've seen computer science professors who are actually mystified by why this is, and students who make this mistake in droves. If I were to write this in Java, the value of this, what it evaluates to, what it turns into, is the value 0. Okay? 1 divided by 3. Why? Because it asks how many times does 3 go into 1 as integers? 0 times. It's not even 1, 3, and 1. There's not even a 1 and 3 inside of 1, and therefore it will replace it with 0. If I write 1 out of 2 in Java, it will replace it's treated as 0. By contrast, if I write 1.0 divided by 2.0, it's 0.5. So, in short, this is integer division. This is integer division. This is integer division. And it will be 0. Now, often that's not what you expect. That's not what you wanted. That's not what you intended. And the way to avoid it is very simple. You just make it clear that at least one of them, at least one, is a floating point number. Okay? So, and to be safe, make both of them. Okay? You don't want a situation where you have, this divided by that or something, and where it won't. But basically, if you want to be safe, put in 1.0. Okay? If you mean 1, put in 1. If you want a floating point number, put in a floating point number. Don't rely on it to do that for you, because you may be bitterly disappointed. And I've seen bugs in models a number of times in my life where that has been the cause. And I will also note that when you convert a model from VenSim into AnyLogic, it imports the equations directly. And if the equation in VenSim is, this is a popular system dynamics modeling package, if the equation is something like 1 divided by 10, it'll turn it into 0 in AnyLogic. And that also is a bug. Okay, in the conversion material. Anyway, ladies and gentlemen, so we have now this as a rate transition with an average time of duration of infectiousness. We could have made it exact, just like we did here, but we choose for variety to have that like that, because often there's a little bit of differences immunologically. And next, ladies and gentlemen, to complete the thought, we're going to have this waning of immunity transition. Okay? Oh, sorry. This one here, good call. I called it nothing. So I will say recovering, and I will put in a name for it so that it is more clear. Again, for stakeholders, it's nice to have names shown. They kind of have a sense of what that means. Okay? And now I will put in a transition back, ladies and gentlemen, from recovered to susceptible. And notice, again, I can bend these things within AnyLogic by putting in these handles here. Okay? Putting in handles. And this transition will be waning of immunity, and it will be given, and I'm going to show the name here. Okay? Showing the name also shows timing statistics on it, time till next time it fires. And ladies and gentlemen, I'm going to make this also a rate transition. It'll be exponentially distributed with a rate of 1.0 divided by main dot duration of immunity. Okay? Notice it's a per day rate, which is what I want. Are we okay with that, ladies and gentlemen? Okay. Great. Okay. Ladies and gentlemen, what else is needed? If this is an infectious transmission model, what else is needed? I would argue one more transition. A transition that may be innocuous visually, but very important for the function of this. Yeah. Internal and infectious to perform what task?
Send messages.
Indeed. So this would be the contact transition. What sort of transition is it? A rate, a timeout, a condition?
Rate.
A rate, indeed. And what's the rate? It is the contact rate. And where does it live? In main. So we have to say main dot contact rate. Right? Are you folks okay with that? Good. And what needs to happen at that contact rate? What needs to be done? If I'm not leaving the state, something should be going on here. Otherwise, it's firing for no reason. What needs to go on when that fires?
Send a message.
Indeed. This dot send to random connected. And I'm going to, now, this is going to need to be changed soon, okay? I'm going to say exposed. Is this going to infect someone? Always? Why not? Suppose it hits upon someone who's not susceptible. It won't infect them then. Suppose it hits upon someone who's susceptible. Will they always be infected?
No.
No. What might happen?
Return to susceptible.
Yeah, they returned to susceptible. They didn't get infected. They were exposed to the bug, but it didn't catch, right? Okay. Good. So, ladies and gentlemen, yesterday, we had us click on a person. Do you remember that to start an infection? Do you remember that? Today, let's suppose that we put in place a mechanism to start with a certain number of people infected. What do you think? Maybe that will be a parameter in main. Number of people, initial number of people infected, you think? Okay, ladies and gentlemen. Okay. So let's go to main and let's add in a count initially infected. Okay? Tempted to say count initially exposed. Okay? But let's give it count initially infected. This is a count, so what sort of type will it be? An integer. You folks are good. And I'll say a default value will be 1. Okay? 1 person infected. Now let's make this happen. Can we make it happen? Okay, now there's several ways to do this. One of them is that in main we could have on startup. Oh, sorry, folks, I should have taken more time. I'm sorry, I'm going too fast. For the palette, I drag this parameter over to count initially, and I call it count initially infected. I made it an integer with a default value of 1. Okay? Are we okay with that? Who needs a bit more time? Okay. Ladies and gentlemen, we're cooking with gas. Okay. Now, there's several ways to do this. We could, in main, we could go and we could have an on startup action. But it's a bit obscure. You can't see visually that it's going on. You have to go look for it or know it's there or go and review the model carefully. So I'd like to add an event, and it's going to be called initial infection event. Okay? Just going to make it more transparent that the infection is going on then. It's just going to be a timeout event. It's going to occur once at time 0. And what's it going to do? Well, it's going to loop through however many times we have to do, and it's going to infect people. Now, you're probably seeing me exhibit pensive features because it's super easy to do this in a most of sort of way. And I'm going to show that first. It's incredibly easy. To do it in a true blown way requires a little bit more mechanism. And I'm contemplating the time and the opportunity cost and so on. let me just do the sort of 99% way, okay? 99.5% way. Okay, ready? Here we go. So I'm going to loop through each person in the population, and I'm going to select, and I'm going to select n random people, where n is given by this number, and I'm going to send the messages to infect them. Okay? Ready? For int I equals 0, I is less than count initially infected, I plus plus, so what this is doing, go through each person population, column person's 0, checking, okay, have we done already, everyone? If not, we'll send that next person a message, and then we'll make I1 bigger, go to 1. We'll check again, are we done? If not, we'll go on and do the next one, etc. So what we're going to do inside this loop is we're going to this dot deliver. Yeah, we have to pick a random city. Okay. Yeah, this is going to be interesting. We pick a random city and then pick a random person in the city. What do you think? Oh, what a thing of beauty. Okay. Oh, there's some nice ways to do that. Oh, man. Why didn't any logic implement another thing a different way? Okay, well, sorry. Okay, so let's get a random city. City, random city equals, and we're going to have cities dot random. Boom. Pick a random city. Within that random city, person, we're going to get a person. Person to infect is going to equal the random city dot population, within the population there, dot random. We're going to get a random person from that population. And then that person, we're going to send a message saying you're infected. Are we okay with that? Okay. This dot send, and what message? So if we look at send, we send a message to an agent. So we're going to send the message, infect, to the agent person to infect.
Exposed, does it make any difference?
Sorry?
Well, if you expose them, they might not become infected.
Well, okay. Yes, so you're getting to the bug that's in this model right now. And we'll see this in a minute. Okay? And we'll fix it. But we'll fix it in a principled way. So we're sending them an infected message. I like.
What's the rest of that? Okay.
Dina is totally on top of things. This is great. So really, I am not being fully. This is not an accurate description. In fact, I can say that, but it's not going to infect them necessarily. Okay, ladies and gentlemen. So I'm going to send an infect message to this person. Okay. Should we run this model? Oh wait, sorry. Just one more thing. Sorry. Yes. Would you like me to put that up on the big screen?
No, just wait for a second.
Okay. Okay. So there's a fly in the ointment because we're going to send them a message, but they're not necessarily going to get infected. So we're going to deal with this in just a minute. But
And when this is looping through, can it send the same person the
yes,
message?
and that's the other fly in the ointment.
Okay.
Now, there are ways that one could do it right that would be, I will show you, okay? and it's not bad. If only AnyLogic Windchill supported streams for population members, you could just ask for the first N people and treat it as a stream and send them a message. It would be a thing of the most exquisite beauty. But they didn't. But it can still be done very beautifully. I mean, it still can be done with high beauty, not just not exquisite beauty.
So we created one where it would pick a random
Yeah.
person, and
Yeah.
then we labeled them, and then we sent it
Correct.
to, so if they were agent 10, then it went to like 11 and 12.
You can do that.
But then that can affect how your system's working. You don't necessarily want to go to the next subsequent agent.
Exactly.
So
Exactly. So you need to do it a little bit with some care. And there's ways to do it. The real question, there's many ways to do it. The real question is how to do it in a crisp way that doesn't involve a lot of mechanisms and doesn't get overwhelming. And doing it in front of a group in that way, it would take a bit of quick thinking on my part. I have some ideas in mind, but because we have such limited time, I don't want to do it right now.
yeah.
Yeah. But you're absolutely right. That is another fly in this ointment. But the bigger fly, that one is like a gnat. The bigger fly, like the horse fly, is that we're sending people a message that doesn't necessarily infect them. And so a lot of them may shed it like water off the back of a duck, and in which case they're not going to be infected. And so we say count initially infected, but we're actually not enforcing it. So what are we going to do about that? Well, ladies and gentlemen, what we're going to do about that is we're going to put in place, ladies and gentlemen, we're going to put in place an option list. Well, let me tell you an anti-pattern. Let me tell you what not to do. Please don't do this, okay? Please don't do this, especially at home. Okay, go to person. What you don't want to do is to make this message, so right now it's unconditional message in person. What you don't want to do is make it contingent on infect versus exposed or something like that. You don't want to do it based on strings. It'll take extra time and it will be fragile. You'll mistype the string in some place. You'll do it with a lowercase e instead of capital E and won't know it's the same string. You don't want to do that. That's an anti-pattern. It's a bad thing with a capital B. Okay? Take it from someone who's been around the bush a few times. So what you want to do instead is let's add an option list. New option list. And this option list will be called messages. I did that a bit quick, didn't I? So new option list, and I called it messages, and I'm going to put things in it. Okay, so let me do that. Let me get rid of this one.
Okay, it won't let me pick new options.
Okay, you want to select the model as a whole.
We're back in projects.
We're back in projects. Select the model as a whole, and do new option list. Okay, we want to call it messages. And we want to have an exposed message and and force infection message. Force infection is for the very specific case where we want to set it up to sort of require that they be infected. Okay? So we're going to have these two messages. And in general, you might have multiple messages. You might have exposed to Hep C, exposed to HIV, exposed to gonorrhea. These are 3 different messages. Okay? Best practice, you have these, finish. Next, ladies and gentlemen, we're going to go to person, and we're going to make the exposure transition here be based on what message, do you think? Which particular message? Exposed. And how are we going to handle force infection? Separate transition. And this transition will be based on a message. And the particular message here will be what? force infection. Force infection. And this will be called, force infection transition. Show name. Okay? Force infection. Good. No, these things are getting a little bit. Okay. By the way, you can. Sure. This one here. This one. So this transition is a message transition. It's called force infection, and it's on a particular message force infection. By contrast, this one is also on a particular message, but it's exposed. So in short, if you're exposed to a force infection message and you're susceptible, you'll automatically go to exposed. No ifs and buts about it. No chance. No chance of not getting infected. If you're getting an exposed message, you have this probability of transmission of getting infected. Are we okay with that? Ladies and gentlemen. Okay, good. So now we have to fix up. Having done that, we have to fix up the two places messages are sent. Where are those places?
Infective and...
Yeah, one is in this contact, right? We're sending a message exposed. What should we be sending now? We sent the message, quote, exposed. That's just a string. It'll be comparing. If we were dealing that, we'd have to compare. What message do we want to send? Exposed. Like that. Exposed. That's for this transition. Contact transition.
Is there any reason you would do exposed versus like messages dot exposed, or how does that work?
So it's a great question. And in some of my boot camps, I'll do messages dot exposed. So messages dot exposed is the general one I like. It makes it very clear it's the exposure with respect to messages. It's a bit wordy. Really where they come different is if there's any clash to another name, if there's another name exposed around. And guess what, folks? There's an exposed state.
Yeah.
So it actually would be, to be clear, it would be better to say messages.exposed. And I'm grateful for you for pointing that out. And similarly, for this guy here, this should really say messages.exposed for this guy here. So let me point that out. So here we have something called exposed as a state. And as a result, if what we mean is send the message exposed, but we say exposed, it's not clear which one it's going to use. And so I would say messages.exposed explicitly and messages.exposed here. It's exposed with respect to this message list, not with respect to this state. Okay? So that's a very good point. Okay? So messages exposed. That's one for this guy here, where it's conditional on a particular message, and then one for this guy here, down at the bottom, which is this guy here, which is messages.exposed. Okay, where's the other place messages are sent right now? And main. Great. On main. So let's go to main, and we have initial infection event, and what do we need to send here?
Force infection, messages dot force.
Yeah, messages dot force infection. So it's good practice in general to be explicit about that. The option list name dot whatever. Okay. Let's build this model. TA stand ready. Who needs TA help? TA help. Summon to the front. Okay? Okay, ladies and gentlemen. What will happen if we run this model now? Will people be getting infected? Well, we can't really see, right? So how are we going to remedy that? How are we going to lend people colors? Can anyone tell me what we need to do here? It shan't take long. What do we need to do?
Create a color.
We need to create a color variable in what? In person. So ladies and gentlemen, let's go back to person. Let's just complete the little exercise. Go back to person. And we'll create a color variable spelled in a Commonwealth way. And what sort of type will this be, ladies and gentlemen?
Other.
It'll be other, and what's the other? Color. No you, indeed. And its initial value, let's make the initial value white, just so they'll stand out. Well, maybe initial value, I don't know. What's the distinctive values?
Lime.
Lime? Lime. Black is kind of going into the connections.
No, let's choose acceptable. Well, you gave us green for our colors.
It was the default. If someone doesn't have a color.
If someone doesn't have a color, we can make them blue because there's no blue planned. It's nice if you choose a color that's not one of the colors that's correct, because then you could spot visually if there's a problem. So let's make it blue because blue is not currently used. Okay, ladies and gentlemen, so color will be a color variable, initial value of blue. Let's set it for susceptible to green. So we added a color variable. We made it blue, right, by default, for the initial value, I should say. And note that the type is other, and it has to be of type color, right? Type, it says other, type color, and initial value blue, ladies and gentlemen, no less. Okay. Next, ladies and gentlemen, I'd like you to go to susceptible, and I'd like you to assign color to be green. I kind of like lime, actually. Should we do lime today?
Yes.
Let's do lime. And then we can pick it to match this, right? Because this is lime.
Yes.
Okay? Ladies and gentlemen, we made color equal to green to the lime for susceptible. Are we okay with that? For exposed, we'll make color be yellow. And for infectious, the color will be red. And for recovered, let's make the color magenta.
The force one. But if you look right above that, there's a pull down that says message. Is it object?
That would be sweet, Winchell. I just realized the best way to do it with Java 8. You do flat map, and then you assign them a random number. You sort them, and you take the first n.
But I see them now.
Yeah, or you just use a shuffle.
So people are all
Yeah,
black.
is there a shuffle built into Java 8 though? I don't.
I think they
Did you
did
tell
have a
them to
shuffle.
become
Okay.
that color?
Okay, that would be
Did
sweet.
you say
Okay,
that?
ladies and gentlemen, we've now set. So we added a color variable, and we set it to be blue by default, and we assigned them to be lime, to be yellow here, and to be red, and to be magenta.
And then they-
Are we okay with that? Okay, ladies and gentlemen. Okay. Okay, so shall we run it? Let's run this thing. Okay. So, has anyone started? Anyone started? I didn't see anyone.
Shape body?
Oh! Thank you. Thank you.
That's why they're black, right?
That's why they're black. Thank you. Okay, so let's go to person, shape, body, and we need to set it to be what? The fill color to be what?
Color.
To be color. Thank you. Color. Color. Okay? Okay. Ladies and gentlemen, we completed the thought. Are you ready now? Let's let it go. Okay? Okay. Okay. Let's run this thing now. Boom. Okay? And we have a bunch of lime green people, right? Okay, I don't see anyone still who's, there's,
It takes a while, I guess they've got to get.
You have to wait for the latent person to.
I guess so. Oh, yeah. Okay, so we can run this here. Now, people are moving a bit fast every 10 days or so, right? Let's slow that down. Ladies and gentlemen, let's go, and because migration event is a parameter in main, how can we change it? Yeah, so let's select a more plausible value. Maybe on a per day basis. Maybe it's 1.0 divided by by 360. So 1.0 divided by 360 times 3. So once every 3 years. Okay. Okay. So here we'll make it much smaller. So they're going to be moving, but it's much less frequent than that. Okay. And we'll do that. Okay. Okay. Now we're cooking with gas.
Can we do a version?
Sure. Yeah. Good call. Good call. Okay, ladies and gentlemen, I changed the migration rate to be 1.0 divided by 365 times 3. So this is once every 3 years they'll move. Okay? Once every 3 years on average. So I'm going to save this away as a new version. Okay? And I will post it here. So, Alan. Okay, oops. Here we go. Oh, it's knocked me offline.
All right, you try.
Unfortunately, I seem to be offline. Is the network working?
Yeah, it's working. I still have too much to.
Okay, yeah, I got knocked off, so unfortunately I can't post this quite yet. Okay.
Do you want to just log into the network, just disable it and try to reconnect? I don't know why it's knocked off.
Okay.
Just turn off the Wi-Fi and turn it on.
Okay, sure. Okay.
Disable it and doing that way again.
Yep. So you have to put in color.
Right.
Okay, good. Good. Let's see. Oh, no, it's unable to.
I guess you still need to connect to.
You have to do that for me.
Okay, now it seems to be connected.
Yeah, you're a little bit far away from the Wi-Fi. That's probably why.
Yeah, I know. I'm wondering if you could bring it up.
I can probably bring in the middle of the room.
That'd be better.
I
Yeah.
try to do that tomorrow.
Yeah. Yeah.
Or during the break I would do that.
Yeah. It's not.
Like, I think probably it's good to go through the tiny URL set rather than. Or
No, I can't post to it with that.
But anyway, it probably takes some time to reconnect to Google Drive.
No,
Yeah.
it's not like it would keep the
Okay.
scale of the
Okay.
people.
Okay, ladies and gentlemen. So if you run this model, what you should see now is a successive, and I'll do it one where it's more visible over space. What you should see is most of the time an initial bug will spread here, and that bug does make it across multiple multiple compartments, or multiple cities here, okay? Let us run an alternative scenario here. We'll copy this baseline and we'll paste in, and we're going to have a low migration scenario, okay? Low migration. And this scenario is going to be associated with a migration every 10 years on average, okay? 10 years on average, low migration. Okay, so now we're going to simulate it. And we get die out of infection here, okay? The infection in this case died out. It did spread initially, but it didn't have enough exposure to new contacts and so on that it led to it to stick. So for the baseline, I had changed migration to be once every. So I'll call this the baseline, and I'd set it to be every 3 years. Winchell, is it possible you could bring that router up, since it is portable, to partway across the room? Because I would like to upload my model. Okay, I'd set it to be once every 3 years. That's what this expression is. Once every 3 years. What's that? And then I made it every 10 for the low migration case. And those led to markedly different outcomes. Let's continue on to look at some additional options here. Okay, so let's take a look at a situation where we have a latency that's longer. So let's look at low migration, high latency. Okay, so we'll do paste here. Okay, low migration, high latency. Okay, and we're going to set the latency to be several weeks. To wit, we're going to set it to be not 3 days, but 21 days. Okay? 21 days here, duration of latency. So while we'll have continued low migration once every 10 years, we'll have a long period of latency, which will mean a long potential time where it's in incubation, right? And there the infection actually persists. It persists despite the low population turnover. Because of the latency, it is remaining in that population for longer periods. Now eventually it may die out through the probabilities involved. I wouldn't be surprised if we ran this for a couple minutes if it died out completely. Okay? Okay, great. Thank you. Will do. Okay, so ladies and gentlemen, here we have a simple model that is obviously fairly scalable. Let's put in place low migration, or let's put in place a baseline but with more cities. So copy, paste, we'll examine, cities, 10. We'll call it 10 cities. You can't say 10 first because that won't please the Java language. You can't say 10 cities. But what you could say is cities, and sometimes I say cities equals 10. Or count cities equals 10. Okay? So count cities here will be 10. And we're going to run this thing with 10 cities. And now we have a larger pool. Okay, this one did not catch. This time it did catch, and we have it circulating over over this larger area. I think it's dying down now, though. I think it actually did die out in this case within a defined time. Sometimes it doesn't take off. It's a probabilistic thing. We have one person initially infected, and it's a little bit dicey about whether it survives. And we could look at varying the size of those cities to see the implications for survival of the pathogen. Okay, ladies and gentlemen, I would like, however, to put in place in our remaining time lenses to capture 2 additional features, if possible. And